Hello, so today we have lesson 4.2 and I'm splitting this lesson into two parts, 2 days. So this is day 1. There's a lot going on in this lesson. And we're going to be exploring the properties of rational exponents and radicals. So we want to be able to use the properties of exponents to simplify expressions with rational exponents. So that's the exponents with the fractions. And we also want to be able to use properties of radicals and write radical expressions in simplest form. So there's a lot of vocabulary words that you're going to be seeing throughout the lesson: simplest form of a radical, conjugate, like radicals, properties of exponents, rationalizing the denominator, and absolute value. So those are things that we're going to talk about in here and within the lesson, and by the time the lesson is over, you should be able to do all of these. You should be able to do these objectives and understand what those words mean. Okay, so we're going to start out just reviewing the properties of exponents. When you first learned how to simplify exponents in your earlier math classes, you've probably seen these rules before. This is called the product of powers, when you take the a to the m power times a to the n power. As long as your bases are the same, when you multiplying, you add the exponents. So here's an example of one with rational exponents. We have a 5 to the 1/2 power times a 5 to the 3/2 power. So you might not have had the rational exponents in the past, but the property is the same as what we did before. So when you have the same base, you add the exponents. So you're going to take your 1/2 and your 3/2 and add them together, which will give you 4/2, which reduces to 2, and then you can simplify if the number's small enough and get 25. The next rule is your power of a power, so a power to a power, where you have a power or an exponent outside of another power. So when you have that situation, a power outside of a power, those powers or exponents get multiplied. So that's your rule. And here we have a quick example of one with a rational exponent. We have a 2 to, so we've got 3 to the power of 5/2, and that whole thing is being taken to the second power. So a power outside of a power, you multiply the 5/2 times the 2, so the 2's actually are going to reduce and just give you 5. 3 to the 5th power, 243. The next one here, power of a product. So if you have two things being multiplied together, taken to a power, you can distribute that exponent or that power to each one of those factors. So it has to be two factors. It cannot be a plus or minus sign in between, so these have to be two things that are being multiplied in order for you to be able to distribute that exponent. So here's a good example. You've got a 16 times a 9 inside of a parentheses. They're being multiplied. They're not being added or subtracted. And you can then take that 1/2 power and distribute it to both the 16 and the 9. So 16 to the 1/2 power and 9 to the 1/2 power are the same as the square root. So the square root of 16 is 4, the square root of 9 is 3, so that simplifies to just 12. All right, the negative exponent. We already saw this in the last lesson. When you have a negative exponent, it does not mean your number is negative. It means the inverse of it, so you're going to put it over 1. So that when you do put that 1 over the a to the m power, that exponent now becomes positive, but notice a cannot equal 0, so that our fraction does not become undefined. So here's a good example, the 36 to the negative 1/2 power. Rewrite it as 1 over 36 to the 1/2 power. 36 to the 1/2 power is the square root of 36, which is 6. So that 1 over 6, 1/6 is our simplified version. 0 exponent, anything to the 0 power is equal to 1, and a cannot equal 0. So even if you have something like 213 to the 0 power, it's always going to equal 1. Quotient of powers. So if you have, you're dividing now. If you have the same base, those exponents get subtracted. And again, your a value or whatever's in the denominator cannot equal 0. So here's a good example. 4 to the 5/2 power divided by 4 to the 1/2 power. The base stays the same. That's real critical. I see that mistake a lot. People want to divide the bases. No, the base stays the same. It's still 4. It's just the exponents that get subtracted. So when you take the 5/2 minus 1/2, you get 4/2, which reduces to 2. Then take the 4 and square it, and you get 16. Going back to this one here, This is a problem where a lot of people want to multiply the 5s together and get 25. Please do not do that. The 5, the base stays the same. It's just the exponents that get added. And last but not least, your power of a quotient. If you have two things that are being divided, that exponent taken to a power, that exponent can be distributed to each of those factors. So the numerator and the denominator will each get taken to that power. Again, the denominator, which is b this time, cannot equal 0. All right, so here's some examples that you can try with me, and we're going to do them together. So we've got the same base of 2, and we're multiplying. So when you're multiplying things with the same base, the exponents get added. So we're going to rewrite this as 2 to the power of 3/4 plus 1/2. So you should be able to add the exponents. So when you add the 3/4 plus the 1/2, if you don't have a calculator, you're going to want to get common denominator. So 4 would be your common denominator. And then 1/2 is equivalent to 2/4. So then when I add the 3/4 and the 2/4 together, that's going to give me 5/4. So 2 to the 5/4 power would be my simplified expression. All right, number 2, or B, letter B. You have 3 over 3 to the 1/4 power. So some of you might be thinking, but that 3 doesn't have an exponent. What are we going to do with that? Well, it actually does have an exponent. Don't forget, if there's a number without an exponent, the unwritten exponent is 1. So now if we write it as 3 to the 1st, we can see, oh, we have the same base. We're dividing. So when the bases are the same, you can subtract the exponents. 1 minus 1/4. Again, in order to subtract those, you would need a common denominator. If you didn't have a calculator that did it for you. So your common denominator would be 4. So 1 is equivalent to 4/4 minus 1/4 would then equal 3 to the 3/4 power. And that would be your simplified expression. Very good. All right, so C is a little bit challenging. I like to throw a challenge problem in there that has a little bit of a twist because we don't have the same base. But these rules can work both ways. Whether you have the same base or the same power, you can simplify it. So looking at this rule here, right here. Okay, yeah, I was looking for it. So the bases here are different, but the exponents are the same, which means we can rewrite this as that fraction, take those bases, make it a fraction, put it in parentheses to that power. So using this rule, going from here to there, the 20 over 5 would be, I can put that in a parentheses all of its own, take that whole expression to the 1/2 power, but then don't forget you've got this -3 on the outside also. So now we're going to simplify this a little bit at a time. So the 20 divided by the 5 would equal 4. And then if I take 4 to the 1/2 power, 4 to the 1/2 power is the same as the square root of 4, which is going to equal 2. So now I've simplified the inside as just 2, and then my exponent to the -3rd power. When I have a negative exponent, put it over 1, so 1 over 2 to the 3rd power, and that 3 becomes positive. Well, 2 to the 3rd is not that big of a number. It's just 8, so we're going to go ahead and simplify that to 1/8. So we had a lot of things going on there, but instead of having the same base, like examples A and B, we had different bases, but the same exponent. So that same rule we can use forward or backwards. Okay, moving on to the next example, letter D. We again, if you look at this example, they do not have the same base. But each of these things are factors, and we have this exponent on the outside. So there is one thing we can do. We can take that exponent, because these are factors, they're being multiplied, you can distribute that exponent to both factors. So what would that look like? It would look like 5 to the negative 1/3 power being taken to the third power times 7 to the 1/4 power being taken to the third power. Now we can simplify each one of these expressions. So now we use the other rule, that's when you have a power outside of a power, you can multiply those exponents together. So negative 1/3 times 3 is negative 1. So that was just going to become negative 1. And then when I multiply these exponents together, I get 7 to the 3/4 power. Well, in a final answer, you should not have a negative exponent. So we can write that over 1 over 5 times 7 to the 3/4 power. We're not going to be able to simplify that. But if we write this now as one expression, the 7 to the 3/4 power would go in the numerator, and then your 5 would go in the denominator. And that is your simplified expression. Good. All right, so letter E. Again, we have a little bit more going on. We're going to have to use more than one of our rules to simplify this. So let's start with the numerator. In the numerator, you have two bases that are the same. It's being multiplied, so we can simplify the numerator by adding our exponents. Okay, so this one I'm actually going to need a little bit of more room, I think, so I'm going to start over here. So the 49 is going to be taken to the power of 3/8 plus 7/8. And then the denominator, I'm going to leave it as 7 to the 5/4 power for now. Not do anything with that. When I add my 3/8 and my 7/8, that's going to give me 10/8. And if you do get a fraction that can be simplified, you definitely want to simplify that. So the 49, now when I reduce that fraction, is going to be 5/4. And my denominator is still 7 to the 5/4 power. Well, how convenient is that? Look at what we have. We have two bases that are different, however, their exponents are the same. So since their exponents are the same, I can rewrite it and put the 49 over 7 in parentheses and put the 5/4 in the power on the outside. So this expression is equivalent to this expression. Well, now the 49 divided by 7 can be simplified to just 7, and then your exponent is still 5/4. So that is our simplified exponent there. So it's kind of like a little puzzle, just working it out until we get our simplified form. All right, going down to the next page now. The next page, I believe, is radicals. So when you have radicals versus the rational exponents, there are a couple properties listed here. The product property, which basically says that if you have two factors that are being multiplied together under a radical, the nth root, then you can separate that radical into the nth root of a times the nth root of b. So here is a good example of what we can do. It's actually backwards. So the same will work here. If you have the cubed root of 4 times the cubed root of 2, notice they both have the cubed root. So since they both have a cubed root, you can actually multiply the numbers underneath, giving you the cubed root of 8. And then the cubed root of 8 can be simplified because the cubed root of 8 is 2. So that worked out nicely. The quotient property, if you have a fraction, so something divided by something else, taken to inside the radical, so you've got the nth root of a over b, that radical can be separated, still is going to be in a fraction, but you can separate it as the nth root of a over the nth root of b. Again, b cannot equal 0 because we don't want a fraction that's undefined. So here's a good example. We have a fraction. The 162 and the 2 are both being taken to the 4th root. So I can rewrite this as the fourth root of 162 divided by 2, which then simplifies to 81, and that can then be simplified to equal 3. So even though it looked kind of complicated in the beginning, we can simplify it till we get a simplified number like 3. So we're going to use those couple of properties in example 2. So in example 2a, these are both square roots, and they're being multiplied. So again, these are things that have to be multiplied. So if you have two things being multiplied that have the same root, you can multiply the numbers underneath, which would give us a square root of 50. Then we want to simplify the radical. So some of you may have not simplified radicals in a while, but when you have a square root, you're trying to find a factor of 50 that is a perfect square. Well, there is a factor of 50 that's a perfect square, 25. So I can factor the 50 into 25 times 2. And then I can separate my square root, my radical, into the square root of 25 times the square root of 2. And the square root of 25 can then be simplified to 5 square root of 2. 2 cannot be simplified. There are no factors of 2 that are perfect squares other than 1, and 1 is not going to help us simplify our radical. So this is now our simplified form. The second example, we again have the same root. So if you have the same root, you can multiply the numbers underneath. Well, before you do that, we probably should look, just like in the last one, could you simplify the square root of 10 or the square root of 5? Well, no, 10 does not have any factors that are perfect squares, neither does 5, other than 1, which we can't use to help us simplify. Well, does 18 or 6, either one of those, have any factors that are perfect cubes? So perfect cubes, 8 is the smallest perfect cube that we could use to help us simplify this cubed root, but 8 is not a factor of either one of these numbers. So that's not going to work. And the next perfect cube would be 27, because 27 is 3 to the third power, and neither one of these are, or both of those are smaller than 27, so obviously they're not going to have a factor of 27. So the only way we can simplify that is by multiplying the numbers underneath and making it one cubed root. So if I multiply the 18 times the 6, I will then get the cubed root of, look at my numbers here, 108. All right, so then you might want to try to find a perfect cube that's a factor of 108. So I would try 8. However, 8 does not go into 108 evenly. So then I would try 27, and 27 actually does go into it evenly. And 27 is a perfect cube. So we can factor that 108 into 27 times 4. And the cubed root of, then we can separate that into the cubed root of 27 times the cubed root of 4. The cubed root of 27 then simplifies to 3, but the cubed root of 4 cannot be simplified anymore, so we're going to leave it as 3. Our simplified answer then is 3 cubed root of 4. All right, well, some of you I know are having difficulty probably figuring out how to break these things down. So one method that I have shown to students is if you're trying to figure out something that's to the third power, a number to the third power that's going to equal 108 or be a factor of 108, you might want to take that number, 108, and do what I call upside down division. So I want to find all the prime factors of this 108. So the smallest prime number is 2. So I'm going to divide this 108 by 2. And instead, I call this upside down division because I want to put the answer, when I take that 108 divided by 2, I'm going to put 54 here. Now I'm going to divide by 2 again, and I'm going to keep dividing by 2 until I can't divide by 2 anymore. So 54 divided by 2 will give me 27. So 27 is an odd number, which means we cannot divide by 2 anymore. Well, the next smallest prime number is 3. So I'm going to divide by 3, which I can divide by 3. and get 9. 9 can be divided by 3 again, which gives me 3. Once you get to a number at the bottom that is a prime number, then you know you've got all the factors, prime factorization of 108. So if I took 2 times 2 times 3 times 3 times 3, that would equal 108. So basically what I have here is 2 squared and 3 to the third. So if I'm taking the cubed root of 2 squared, not cubed, I was thinking ahead. It doesn't want to erase. All right, so 2 squared times 3 to the third, because we do have 3 3's here. So that's your 3 to the third right here. And we separate that. Try not to run into this other one. So we can separate that as the cubed root of 2 squared times the cubed root of 3 to the third. So the 3 to the third, so that third root and that third power will cancel each other out, which gives us just 3 times, and then we can't, since you do not have 2 to the third power, you can't reduce this, so then we would just multiply it back together, 2 squared, which would be 4, but it's still a cubed root. So that does equal the same thing that we had just a minute ago. So I don't know if that's helpful, but you can use that that method to help you find your prime numbers or prime factors of something, to help you factor or help you simplify your radicals. All right, so moving on to letter C. So in letter C, you have the cubed root of 9 times the cubed root of 6 in the numerator, and then you've got the 6th root of 2 times the 6th root of 2 in the denominator. So we have basically the same root, but different numbers underneath. Here we have the same root and the same numbers underneath. But anyway, we're going to rewrite this. I'm going to need some extra space here, so I'm going to move it over here. Because we have the same root, I'm going to multiply the numbers underneath to get the cubed root of 54. So 9 does not have any factors that are perfect cubed, either to 6. However, when we multiply them together and we get 54, that 54 has a factor of 27. So we can separate that factor, that cubed root of 54, into the cubed root of 27 times the cubed root of 2. Okay, so the denominator now, notice you have a 2 here. So I'm going to want to keep that 2. We're going to have to be a little bit creative here. So that 2 and that 2 multiplied together, instead of getting 4, I am going to leave it as the 6th root of 2 squared. So one thing that you're going to want to do when you see these roots and these powers, and you notice they can be reduced. Just like in the last, on the last page, we had, where is that one that we reduced? Here. So when you have an exponent that is a 10, the power is 10, the root is 8, when you have a fraction here that can be reduced, you definitely want to reduce it. Well, the same thing is true with radicals. So if you have a root and a power that can be reduced, it's the same as rewriting this as 2 to the 2/6 power. Well, 2 to the 2/6 power would then simplify to 2 to the 1/3 power, which is the same as the cubed root of 2. You could also have just reduced these here, the power and the root, since they both can be divisible by 2. If you divide both of them by 2, that also would give you the cubed root of 2 to the 1st. So if I divide this by 2 and that by 2, this becomes 3, that becomes 1. The 1 is insignificant, but what is important now is that we can reduce in the numerator and denominator that cubed root of 2. So let me use a different color. So that can reduce. And then the cubed root of 27 is 3. So our simplified answer is 3. All right, so that's a few of those. Hopefully that made a little bit of sense. But here's how we got from here to there, in case you're wondering. But you can just reduce the power and the root right here and put it here. You don't necessarily have to rewrite it as a fraction and then reduce it. But if it helps, then go ahead and rewrite it as a fraction and then reduce. Okay, in example 3 now, we are talking about simplest form, and that was one of our definitions that we had on the first page. Where's my pink? So simplest form. When you have a radical expression in simplest form, that means it must meet the following conditions. So number 1, no radicands have perfect nth powers as factors other than 1. So the radicand is the number that's underneath. So when we simplified this 108, we had to simplify that. In order for this to be in simplest form, that 108 could not have any perfect cubes that are factors of 108. So we took care, so this no radicands have perfect nth powers, so 27 is basically 3 to the 3rd power. So we can't have any perfect cubes that are factors of this 108 other than 1. So if you look at our final answer, 4 does not have any factors that are perfect cubes that we can reduce. So that's what that first rule is telling us. Secondly, there can be no radicands that contain fractions. So you cannot have a fraction underneath, or so if this was like a cubed root of 2/3, you could not leave your answer. Your answer would not be in simplest form if you have a fraction in underneath the radical or in the radicand. And then thirdly, you can have no radicals in the denominator of a fraction. So these next few examples, we're going to be focusing on making sure that it's in simplest form, which means no radicands have, so no perfect powers or no perfect squares, no perfect cubes underneath the radical, no fractions under the radical, and no radicals in the denominator. So when we look at our first example, we're going to write these following in simplest form. We have a square root of 32 over 3. So that conflicts with rule 2 here that says no radicands contain fractions. So right now the radicand is 32 over 3. That is a fraction. So you cannot have a radicand that is a fraction. 32 does not go into 3, so we can't reduce that fraction, but we can separate the square root. When we separate the square root with the numerator, between the numerator and the denominator, and rewrite this now as a square root of 32 over square root of 3, we can then simplify or rationalize the denominator. So you may need to rationalize the denominator by multiplying an expression by something that's going to make this radical go away. So when it's a square root, you basically, when your root is 2, you basically need a 3 to the 2nd power. So you're going to multiply by another square root of 3, but you can't just do that to the denominator, you have to do it to the numerator also. So we're basically multiplying by 1. So that's what this is saying right here. You're multiplying by the expression that's equivalent to 1 that is going to eliminate the denominator. So the square root of 3 over the square root of 3, that is equivalent to 1, but it's going to help us rationalize this denominator. So now if we look at it, we've got the square root of 32 times the square root of 3. I'm just going to leave that there. I'm going to simplify the numerator in just a second. But if we simplify this, the square root of 3 squared, so that 3 times that 3 gives us 3 squared. So if you have a square root, you want something to the second power to reduce it. So the power and the root cancel each other out, giving you a denominator now that's just 3. In your numerator, 32 times 3, we can multiply that together. Or we could simplify the square root of 32 first, but we'll go ahead and multiply it together and then simplify it. Actually, no, let's take your 32 and factor it. So hopefully you're thinking 16 in your head. 16 is a perfect square. That's a factor of 32. So I can factor the 32 into 16 times 2. And then since these are both square roots, I can put that 3, multiply that 3 underneath also. So when I simplify the square root of 16, I'm going to get a nice whole number, 4. But the 2 and the 3 are not perfect squares. Even if I multiply them together, I get 6. 6 is not a perfect square either. So that is going to have to stay under the radical. My denominator, however, is going to remain 3. So we got rid of the fraction in the radicand, and we got rid of the radical in the denominator. So this is now in simplified form, or simplest form. Okay, if you need help simplifying radicals or square roots, we can spend more time on that in the morning if you'd like to come before school. But for right now, we're going to move on to the next one because we have a fourth root. So when you have a fourth root or a third root or a fifth root, when it's square root, you just learned to multiply it by itself because you'd only needed 2 or a power of 2. Well, when you have a fourth root, you need to have something to the fourth power. Well, rather than just taking this 9 and multiplying by 9 to the third to get a 9 to the fourth, one thing you can do is ask yourself, is 9 a power of any other number? Well, yes, 9 is a power of 3. So I could rewrite that denominator. So you have to be creative when you're doing these problems. And there's a lot of calculations going on in your head. So 9 could be rewritten as 3 squared. So that 3 squared can now be reduced. We can reduce the 2 and the 4, the power and the root, and instead of a fourth root now, we're going to have a square root because that's going to become 1 and this is going to become 2. So we were able to reduce the 2 and the 4. Well, we're still breaking one of the rules. We still have a radical in the denominator. But now we just, instead of having to multiply by something to make it a perfect fourth power underneath, we're going to multiply by just another square root of 3. Oops, not third root. So this is a square root of 3. Now, some of you are probably thinking, do we have to put the 2 there? No, you don't, but it does kind of help sometimes when you're trying to simplify these things. So when I rewrite this, rather than multiplying that together and getting 9, so I'm going to bring this down here. I'm going to rewrite the denominator as the square root of 3 squared so that you can see that that square root and that square are canceling or eliminating each other or undoing each other, and that simplifies to just 3. Now in the numerator we have a bit of a problem. We've got the fourth root of 19 times the square root of 3. And because these are not the same root, we cannot multiply those numbers underneath. Well, is there something that we could do to change this so that it would have the same root? Well, yes. Earlier we had rewritten the fourth root of 9 as the fourth root of 3 squared, which reduced to the square root of 3 to the first. So that square root of 3 to the first, we can now go backwards and rewrite it as the fourth root of 9. So the fourth root of 19 now we can multiply by the fourth root of 9. So that square root of 3 I rewrote as fourth root of 9. Again, it's because if we worked backwards, I could take that power and that root, multiply them both by 2, which gives me 2 and 4, and then that 3 squared simplifies to 9. The whole point of that was to get the same root so that I can then multiply the 19 and the 9 together, giving me a final simplified answer of fourth root of 171 over 3. So yeah, that one was a bit complicated. I might have chosen a different way to do that next time, but there are many different ways usually to simplify these radicals. But as long as you follow your rules, your algebraic rules and your properties, you'll get the same, you should end up with the same simplified version at the end. Okay, the last problem here, letter C, again we have the same root, but the numbers underneath, I could rewrite this and simplify those numbers underneath a little bit. So let's do that. If I rewrite this as the fifth root of 14 over 8, I can then reduce that as to 7 over 4. But we cannot have a fraction in the radicand, so I'm going to actually have to separate it again. But at least my 14 and 8 reduced a little bit. Okay, so now we have to figure out what can I multiply this by to get a perfect fifth power, because the only thing that's going to simplify with a fifth root is something to the fifth power. Well, let's think about 4 for a second. Is 4 a power of something? Yes, 4 is a power of 2. So just like before, I'm going to rewrite the 4 as 2 squared. Now, how does that help me? Well, what I want to get is I want to get a fifth root of 2 to the fifth power in the denominator. That's what I want, so that the fifth root and the fifth power will cancel each other out. Well, if 4 is already 2 squared, then what I need to multiply by is 2 to the third. So the fifth root, the fifth root of 2 to the third. So that 2 squared and that 2 to the third, when I multiply those together, will give me 2 to the fifth, which will then reduce with the fifth root. So that's how you rationalize a denominator when you have a power or a root other than 2. Keep in mind, though, we have to multiply by something that's equivalent to 1. So if you do it to the denominator, you have to do it to the numerator also, so that technically this expression that we're multiplying is equivalent to 1. So now our denominator is what we wanted it to be, the fifth root of 2 to the fifth. In the numerator, we have fifth roots, so they're both fifth roots, so we can multiply what's underneath. So the 7 times the 2 to the third, well, 2 to the third is 8. 8 times 7 is 56. So in the numerator, I'll have the fifth root of 56. And then in the denominator, I can now reduce the fifth power and the fifth root. So my final simplified answer is the fifth root of 56 over 2. And there we have it, our simplified answer. There's no, so again, how do we know it's simplified? We do not have any radicals in the denominator. We do not have any fractions in the radicand or underneath the radical. And there are no fifth powers that are factors of 56. So those are your 3 rules for simplifying or putting it in simplest form. Okay, moving on. Example 4. Sometimes you have denominators that instead of just having a one term that's a radical, you have a binomial that has a radical, or a binomial that has two radicals. And these things are being added or subtracted. So when you have something like this, you have to, again, multiply by something we cannot have a radical in the denominator. That's not going to be in simplified form or simplest form. So we need to figure out, well, what can we multiply this by to get rid of that radical? And back in the last course, in chapter 2, I believe it was, or maybe it was 3, we learned about conjugates. So we have a conjugate of the square root of 7 minus 2 has a conjugate. It's not a complex conjugate. It's the word is not coming to me. Anyway, it's conjugate. I can't think of the term that I'm looking for. It'll probably come to me later. But the conjugate, basically the first term stays the same, but the sign is going to be the opposite. So your first and last terms basically are the same values, but your signs are going to be opposite. Now, why do we need to multiply by that? Well, we'll show you in just a second when I multiply those together. So down here, if I multiply, I'll show you what it looks like. Let's focus on the denominator. So if I take the square root of 7 minus 2 times the square root of 7 plus 2, you've got basically a binomial times a binomial. So when you have a binomial times a binomial, usually we FOIL or distribute the first term to both of the terms in the other binomial, and then the second term gets distributed to both terms in the other binomial. So the square root of 7 times the square root of 7 would equal the square root of 7 squared, or you could say the square root of 49. Either way, that's going to reduce and give us 7. The square root of 7 times positive square root of 2 will be plus or positive 2 square root of 7. Since the 2 is a whole number and the square root of 7 is under the radical, these numbers cannot be multiplied together. So the 2 just would go in front, and then your square root of 7 would go after it. Now we're going to multiply the inside terms. Negative 2 times square root of 7 is going to be a negative 2 square root 7. Well, what's nice now is the positive 2 square root of 7 and the negative 2 square root of 7 are going to basically cancel out, because if we, just like combining like terms, if you have a positive 2x and a negative 2x, that gives you 0x. Well, if you have a positive 2 square root of 7 and a negative 2 square root of 7, that's going to basically be a 0 square root of the 7. So 0 times square root of 7 is just going to be 0. But don't forget about the last term. The negative 2 times the positive 2 is going to be a negative 4. So when you FOIL this out, these are your 4 terms that you get. The square root of 7 squared, or the square root of 49, is 7. The middle terms cancel out, and then you have this minus 4. So when we simplify that, now we get 3. So our denominator is just 3. But you do have to do this multiplying work down here to get that 3. All right, in the numerator, well, this expression right now, the way it's written, is not equivalent to 1. So in order to make this equivalent to 1, you have to put the square root of 7 plus 2 in the numerator also. So the square root of 7 plus 2 over the square root of 7 plus 2 is equal to 1. That 1 here, now you're just going to multiply your numerators together. So 1 is a nice number to multiply by, because anything times 1 is itself. So your numerator is just going to be square root of 7 plus 2. So now it is in simplest form, because we've gotten rid of the radical in the denominator. There are no fractions in the radicand, and there are no perfect squares that are factors of 7 underneath. So that's simplified form. All right. The next one, 4b. Now we have 2 square roots. But that's not an issue. We're just going to multiply by its conjugate. So the first term and last term basically stay the same, square root of 5 and square root of 6, but instead of adding, now we're going to subtract because we want that middle term to cancel out. And whatever you do to the denominator, you have to do to the numerator because this expression has to equal 1. So this, it has to be equivalent to 1, which it is if you have the same thing divided by itself. Now let's look at the denominator. What's going to happen when we multiply that denominator together? So off to the side here, I'm going to take my square root of 5 plus square root of 6 times the square root of 5 minus the square root of 6. Now eventually, once you start multiplying these things together, and you've done it quite a few times, you can start skipping a few steps. But for right now, I would like for you to have all 4 steps written out. So that square root of 5 times that square root of 5 will be the square root of 5 squared. The square root of 5 times a negative square root of 6. Because these are both square roots, you can multiply the numbers underneath, but it's going to be a negative square root of 30. And then we distribute this square root of 6 times that square root of 5. Again, they're both square roots, but you have 2 positive numbers being multiplied together. So it's going to be a positive square root of 30. And then the positive square root of 6 times the negative square root of 6. Be careful with your signs here. Positive times negative is negative. Square root of 6 times square root of 6 is square root of 6 squared. Or you can multiply those together and get square root of 36. Either way, it's going to reduce. So the square root of 5 squared, or the square root of 25, whichever you have written, reduces to just 5. The negative square root of 30, the positive square root of 30 cancel out. And then your square root of 6 squared, or the square root of 36, will just equal 6. So we basically have this 5 minus that 6, which is going to equal negative 1. So that is now our denominator. So that negative 1 goes in the denominator. And this 3 went in the denominator over here. So going back there so that you can see where that 3 came from. So all of this is simplifying the denominator. Now your numerator, we're just going to multiply across. Since these are not like terms, the only thing you can really do is distribute the 8 to both of those values. You may even be able to leave it in factored form, but we're going to go ahead and distribute. So the 8 times the square root of 5 is just 8 square root of 5. The 8 times the negative square root of 6 is negative 8 square root of 6. And the square root of 5 and the square root of 6 are not like radicals, which means we cannot simplify them. However, you don't really want to leave a dividing by negative 1. Okay, so there is one more step here to go. When you divide by negative 1, that's going to change both of your signs or change the signs of any terms that you're dividing. So if I divide the first term by negative 1, I'm going to get negative 8 square root of 5. If I divide the negative 8 divided by negative 1, I'm going to get a positive 8 square root of 6. So that is even more simplified. Again, you're not going to want to leave a denominator of negative 1. So this is our simplified answer. All right. So almost done. We've got example 5 to go. And these are adding and subtracting like radicals or roots. So notice you've got radicals here, you've got rational exponents here. So whether you have a radical or a rational exponent, the way that you're going to simplify these are very similar. And it might be easier, actually helpful to change those to radicals. Actually, I'm looking at my notes from last year, and no, I'm going to leave those the way they are. Okay. So look at example A. You have a square or a sixth root of 17 plus 9 sixth root of 17. So if you have a radical that has no number in front of it, basically it's like having a coefficient of 1. And if you look at both of those terms have a sixth root of 17. So it's kind of like you have like terms here. If you had a 1x plus a 9x, it would equal 10x. Another way of looking at it is if both terms have a sixth root of 17, we can say factor it out. So the 1 plus 9, if I factored out, I'm going to put it at the end though. So I'm factoring out the 6th root of 17. So if I factor out the 6th root of 17 from this term, that's going to leave me with 1. If I factor out the 6th root of 17 from this term, I get 9. And then if I add the 1 and 9 together, I just get 10 6th root of 17. But you can only add those coefficients if the root and the radicand are exactly the same. So in this next problem here, the exponent is the same, but the base is not. So we have to somehow make this expression, simplify this expression so that we have a 7 to the 1/3 power, if possible. Well, how can we do that? Well, here we go. So the 5 is already a whole number, so we're going to leave that out front. But we're going to factor the 56 into two numbers, and one of the numbers is going to be a perfect cube. So our root here is 3. So the only way we can simplify a cubed root is if we have something that's a perfect cube, or something that's to the 3rd power. Well, 56 can be factored into 8 times 7. So I'm just rewriting this expression, 56, as 8 times 7, but it still is equivalent to what I had prior to that. Well, now that I've factored the 56 into 8 times 7, I can then distribute that 1/3 to both of these factors. So I'm, again, using all the properties of exponents. So I'm going to distribute that, and again, you can only distribute it when you're multiplying, when these are factors, or if you're dividing. So 8 to the 1/3 power times 7 to the 1/3 power is what we have now. So we have to be creative with this, and we have to kind of work it out. This 8 to the 1/3 power now is the same as a cubed root of 8. The cubed root of 8 is 2. So that cubed root of 8 becomes 2 because 2 to the 3rd power equals 8. So now we can multiply our whole numbers together, the 5 and 2, and get 10 times, and I'll put this back in parentheses, 7 to the 1/3 power. So all of that was just simplifying that first term. Well, now that we have 10 times 7 to the 1/3 power, and if we bring this expression down, this term down, 6 times 7 to the 1/3 power, well, the 7 to the 1/3 power they have in common. So I can add my coefficients. So these are what we call like radicals. So, or they have the same rational exponent. Oops, I guess really doesn't matter whether the parentheses are inside or outside with this problem, but to make it look the same, I put the 1/3 on the outside. So it's exactly the same as if you had 10x plus 6x. You would add the 10 and the 6 together and get 16x. Well, instead of x, we have 7 to the 1/3 power. So this is going to be equal to 16 times 7 to the 1/3 power. And like I said before, it's kind of like if you factored that 7 to the 1/3 power out, you would have 10 plus 6 left over, which would equal 16. So that is our simplified radical. Okay, one more to go, and then we are done with our notes. So this might take a day and a half to get through these notes. So here we have another expression. We're subtracting now. We cannot subtract, though, unless these radicals are the same. So we have a 4th root of 3 here. The 4th root of 3 cannot be simplified because 3 is a prime number. There's nothing that we can take to a 4th power that's going to give us 3. So we have to then work with the 48. So we may, like before, this might help to have to break this down into its prime factorization, because we need to basically find a number that to the 4th power will be a factor of 48, so that we can reduce it with this 4th root. So starting with 2, which is the smallest prime number, I'm going to divide the 48 by 2. I'm going to use a different color so you can see the difference here. So when I divide 48 by 2, I will get 24. Well, 24 is still an even number, so I can divide by 2 again. So 24 divided by 2 gives me 12, which is still an even number, so I can divide by 2 again, which will equal 6, which is still an even number, so I can divide by 2 again, and then last but not least, I get 3, which is a prime number. So 48 can be rewritten as 2 to the 4th power times 3. So I'm going to rewrite this expression as 2 times the 4th root of 2 to the 4th power times 3. So that 2 to the 4th power times 3 is still equal to 48. So we didn't change the value, we just changed the way it looks so that we can simplify it. So now if I separate that 4th root as 4th root of 2 to the 4th times the 4th root now of 3. So I'm just taking those factors and factoring it and separating that 4th root. That 4th power and that 4th root will cancel each other out, giving me a nice whole number of 2. So that 2 and that 2 can multiply together, which gives me then 4. And I can keep carrying this 4th root of 3 down. So this 2 times 4th root of 48 simplifies to 4 times the 4th root of 3. Now bring down your second term. That was already simplified. And notice again, we have a 4th root of 3 here, we have a 4th root of 3 here. So when those are the same, it's kind of like having a 4x minus a 5x. You just combine you add the coefficients. So the 4 minus the 5 is -1, and because we have the same 4th root of 3, that stays the same there. So that is the end of the notes for 4.2 day 1.